Welcome back to another great section of this wonderful tutorial class. We are excited or super excited to have you guys back. Now remember not to distract yourself by any means as you are watching this video, and ensure you watch the video to the end. Don't skip any part of the video in order to get the full details of everything we'll be explaining in this wonderful class. Now this engine installing or tutor is God's love, and I'm here to show you guys some vital information concerning the subject or the course. It's called physics. You know, physics is a very important course in science, and it is a pure science. And today, there are some things that we call physical quantities that some students don't even know. And there's what we call dimensional analysis of physical quantities that some students don't still know. So these things ought to be known by students. So that's why we are giving you guys this class, to know about the aspect of experimental observation, to know about the what we call units, to know about what we call physical quantities and their dimensional analysis. So please stay with us to the end of this video in order to get the full details of everything we are going to be doing here. Now, remember to subscribe to this channel if you have not done so, because it's very important to subscribe. As our subscription keep on increasing, we'll have more strength to doing more videos. Thank you guys as you do that. Thank you very much. So please, let's move to what we have for today. Now, we have the dimensional analysis of physical quantities. Now, the first thing is, what is the meaning of physical quantities? What is the meaning of physical quantities? We're going to look at that. But before we go to that, please take note of these things. Now, there are three basic aspects you write. Now, I would like you to have a note, because this is a class. It's not just a video for fun or a video for entertainment. We are not entertaining you guys. We are teaching you guys. We are teaching you guys. Alright. So please, I would like you to have a note when you're using for this class. It's very important. Now, there are three basic aspects of experimental observation. We have three basic aspects of experimental observation. There's what we call measurement. The first one we call it measurement. The second one we call it uncertainties. And the third one we call it correlation. Now, what's the meaning of measurement? Measurement means the quantification of observation. When you quantify what you have observed, when you are quantifying what you are observing, that process is called measurement. You are measuring it. You are measuring what you are observing. It means you are quantifying it. You are giving it a quantity. You are giving it a value. That's what it means. Now, there's another thing that is called uncertainties. There's another thing that is called uncertainties. Now, what's the meaning of uncertainties? Now, uncertainties are just errors that can be found in measurement. Now, every measuring device has a little amount of uncertainties that, if it is not known, we'll be calling them errors. We call them what? Errors. So, uncertainties are just like errors that are known. If you don't know them, you can just call them uncertainties. But if you don't know them, we can call them errors. Errors found in measurement are called uncertainties. Then there's this third aspect of experimental observation that we call correlation. We call it correlation. Now, what is the meaning of correlation? What is the meaning of correlation? Correlation is the degree of regularities between measured quantities. Is the measure of how regular what you are measuring is. The degree of regularities between measured quantities. That's what we call correlation. So please take note of these three aspects of experimental observation: correlation, measurement, and uncertainties. So please, it is very important. Now, in physics, there's what we call physical quantities. We have called physical quantities. Now, what is the meaning of physical quantities? It's very important. What do we mean by physical quantities? Now, all measurable quantities in physics are called physical quantities. I repeat, all measurable quantities in physics or all measurable quantities in science, we call them physical quantities. Now, all these physical quantities can be presented in two ways. We can present them in what? In two ways. Now, how we call fundamental quantities and what we call derived quantities. What we call fundamental quantities and what we call derived quantities. So physical quantities can be divided into two. They can be divided into fundamental quantities and it can also be called derived quantities. Now, when are they called, or which of them we call fundamental quantities and which of the physical quantities we call derived quantities? So take a look at this question. Take a look at this question. All quantities in physics are called physical quantities. You take a look at that, it's very important. All quantities in physics, all measured quantities in physics are called physical quantities. So please take a look at that, it's very, very important. Now, what is the meaning of derived quantities and what is the meaning of fundamental quantities? Now, derived quantities, let's start from fundamental quantities. It's very good to start with that, please.
Fundamental quantities are quantities that don't depend on any other quantity.
Let me repeat so that you understand this better. Now, fundamental quantities are quantities that don't have proof. They are quantities that are intuitively known. They are quantities that forms other quantities. If you combine two or more fundamental quantities, you're going to have other quantities. Now, example of fundamental quantities are mass, length, time, luminous intensity, thermodynamic temperature, amount of substance, current, etc. We call them fundamental quantities. Now, the units of fundamental quantities are called fundamental units. Take note of that. The unit of what? Fundamental quantities are called fundamental units. Now, what is the meaning of, what are some examples of fundamental units that we have? Now, for mass, the unit of mass, the system international unit of mass is kilogram. Although you can use there are other units you can use, but the system international unit used in physics is the SI unit, is the what we call kilogram. Then for length is meters. For time is seconds. Time is a fundamental quantity. Length is a fundamental quantity. Mass is a fundamental quantity. Please take note of that. It's very important. Now, for luminous intensity, that is still a fundamental quantity. The unit is candela. Then, another one is volts. Then, current is ampere. Current is ampere. That is still a fundamental quantity. Then, thermodynamic temperature is Kelvin. That is the unit. So please take note of those things. They are very important. Now, there's what we call derived quantity. Derived quantities. Now, what are derived quantities? What are what? Derived quantities. Derived quantities are quantities that are formed from the combination of two or more fundamental quantities. Derived quantities are quantities that are formed from the combination of two or more fundamental quantities. So if we combine two or more fundamental quantities, we are going to form what we call derived quantities. Now, what are some examples of derived quantities? We have what we call velocity, weight, force, acceleration, and so on. They are called derived quantities because they are formed from a combination like velocity. Now, velocity is formed from combination of displacement and time. Velocity is the rate of change of displacement. Please, if velocity is equal to displacement over time, we have displacement and then displacement is measured in meters, then time is measured in seconds. So you combine meters and seconds together, you take the quotient, you know how we call velocity. So acceleration is the rate of change of velocity, which is the velocity over time. Some of the units of derived quantities, the unit of derived quantities are called derived units. They are called what? Derived units. Some of those units are for velocity we have meter per second, for acceleration we have meter per second square, for weight we have newtons, which is somebody's name, and that newtons is equivalent to kilogram meter per second square. So please take note of that. It's very important. It's very, very important. Now, what is the meaning of non-dimensional analysis of physical quantity, or the dimension of a physical quantity now? Now let's go to the dimension of physical quantities. Now, the dimension of physical quantities, shows how an equation relates to its fundamental quantities. Shows how an equation relates to its fundamental quantities. Now, what I'm trying to say is that I have mentioned some fundamental quantities, I said some examples of fundamental quantities can be mass, length, and time. Though we have others. We have current, we have electrical. So let's just start with those three. So these and these are fundamental quantities. Now, dimensional analysis now will now show how a particular equation or how a particular formula relates with each fundamental quantity. Because some things you will see inside that formula might not be fundamental quantities. So you will break them to show us how that equation relates with its fundamental quantities. That's what we are doing in dimensional analysis. And the dimension of the following fundamental quantities are as follows. Now, the dimension of mass, not unit. Please take note of dimension and unit. We have the dimension of a physical quantity and we have the unit of that physical quantity. They are not the same. Now, the unit of mass is kilogram. That is the unit of mass. The unit of length is meters. The unit of time is seconds. But the dimension of mass is capital letter M. Take note of that, it's very important. The dimension of length is capital letter L. The dimension of time is capital letter T. Please take note of that. The unit of mass is kilogram. The unit of length is meters. The unit of time is seconds. These are just symbols for the unit. They are also this is symbol for kilogram, the symbol for meters, the symbol for seconds. You can go and look at the full spelling. That's what we are doing here now. But for dimension, because the dimension we are looking at, dimension is for mass is capital letter M. For length is capital letter L, for time is capital letter T. Now, what am I trying to say? Anything that has units as meters or metric units, the dimension must be L. That's what I'm trying to say. Anything that has units as seconds, the dimension must be T. Anything that has units as mass, kilogram, the dimension must be capital letter N. Please think of that. It is very important. Now, for example, what is the unit of radius? Just radius. Or what is the unit of diameter? Their units are measured in metric, which is either centimeters, meters, millimeters, so on. Then the standard unit will now be meters. Now, there are what we call, please take note of this. There are what we call orders of magnitude in physics. Orders of magnitude in physics. We have small values, we have the large values. For example, I don't know if you are hearing millimeters. I don't know if you have heard about that before. Centimeters, decimeters, kilometers, megawatts, megabyte, terabyte, kilobyte. I don't know if you have heard about those things before. Microwave, micrometers. I don't know if you have heard about those words before. Now, all those kilo, micro, milli, deci, centi, they are called, they have magnitude. For example, what we call means kilogram. This K means kilo. This G means gram. The value of this kilo is 10 raised to power 3. That is one of that kilo. So kilometers is 10 raised to power 3 meters. That's what I'm going to say. It's what we call microcoulomb. Microcoulomb. This is symbol for micro. Now the value of the magnitude of micro is 10 raised to power minus 6. So the coulomb is used for charge. Coulomb is used for charge. Now, if you want to write some charges because they are very small, you write it in terms of all these magnitude. Because we have millicoulomb, we have microcoulomb, we have nano. There's another one called nano. Like those smaller than coulomb. Nano is a value that is 10 raised to power minus 9. That is the name we use to 10 raised to power minus 9. So anytime you see 10 raised to power minus 9, yeah, you can think of it nano. It's just smaller than 10. So please think of all those orders of magnitude. It's very important. You can also research more Then it's very important when we come to physics. It's very important. Now let's go back to our dimensional analysis. I already said the dimension of mass is m, the dimension of length is m, then the dimension of time is t. Taking of those things is very important. Now, before we go, let us look at a few examples to know what we are doing. Now, derive or obtain the dimension of the following physical quantities. Example: obtain the dimension of the following physical quantities. Obtain the dimension of the following physical quantities. Obtain the dimension of the following physical quantities. So, number one, velocity. Velocity. That is the first one we're going to look at. The dimension of velocity. Now, what is the dimension of velocity? Look at how to calculate for dimension of physical quantity. The first thing you say is, you just don't forget, what is the definition of velocity? Velocity is defined as the rate of change of displacement or displacement over time. That's what we call velocity. Displacement over time, which is can also be displacement with x over time is t. Now you're like, okay, what is the unit of displacement? Displacement is measured in meters. Now I already told you anything that is measured in meters. Just like remember the unit of length is meters, unit of this one is kilogram, unit of time is seconds. Please take note of that. Now I already told you anything that is measured in meters, the dimension must be L. So since displacement is measured in meters, the dimension will be L over. Now, what is time? Look at time. What is the dimension of time? T. So this is the dimension of velocity. We just break everything in the equation down to their fundamental quantities. When you are going to their fundamental, in which all the quantities there, they are not fundamental quantities, you are good to go. Now, let's put this one in another form. Let's apply this. Also, you have L. Then this one is t raised to power 1. Now look at something. In the something I'm going to show you guys now. In mathematics, we have to like this. Let's say we have a raised to power m over b raised to power n. Now, if this a move from this top to this down, or this b move from the down to the top side, the sign of this power will change. Look at what I mean. If I decide to move it downward, I decide to move it downward and bring this b upward, it will not be like this. B raised by the power will change sign. If it was positive before, we change to negative. If it was negative before, we change to positive. So this m, since that value of this m went to minus m, then if this a comes down, the m will change to this m will change to minus m as well. This power will change sign. If we can change the denominator and the numerator. If you still move this one upward and bring this one downward, things will change back to their original power. Let's have 1 over, let's say b raised to power minus n. If you want to move this one upward, because if you bring this one down, even though you have 1 square minus 1, it's still 1. 1 square, any power is still 1. So that's why that one don't actually affect. The other things will affect. So if you have to move this one upward, or to move b upward, this sign will change from minus to plus, or from plus to minus. It's already minus 2 to plus n. That's what we are going to have. And over 1. So this will minus 1 minus 1 because 1 is raised by 1 already. This one is minus 1. If we have 1 minus 1, it still will be 1, and it will never affect anything. So please think of that. It's very important. It's very important. So if I move this here upward, this power will change sign from positive to negative and from negative to positive. It was already positive before. I already told you any number that don't have power is only power that's raised to power 1. So I have t. This one will change to minus 1. So that's why I this one. Because this one is not going up. So this will change to minus 1. If you decide to bring this L down, this L is raised to power 1. We try to minus 1 as well. We are not bringing the L down. We are trying to bring the T up. So the dimension of velocity is either L over T or L to this power minus 1. So please take note of that. Now number 2. The dimension of acceleration. The dimension of acceleration. Dimension of acceleration. The dimension of acceleration. Dimension of acceleration. So acceleration is equals to the rate of change of velocity or velocity over time. That's what we mean by acceleration. That's what we mean by acceleration. Velocity over time. The velocity over time. Velocity over time. So what is the I told you if you want to find dimension, we break everything down to their dimension. That's it. What is the dimension of velocity? Well, the velocity is L to the power minus 1. So velocity is LT raised to the power minus 1. That is the dimension of velocity. Then over what is the dimension of time? T. Then this one is raised to the power 1. I will tell you. The next, I want to move everything upward. I will have L. Remember, look at it. I will show you if this one move up now. What will you tend to? If this one decide to move up, then what? Minus 1 as well. And that one is there. Then remember another thing. I told you if you have L raised to power, if you have A raised to power n divided by A raised to power n, you can have T raised to power minus 1 divided by T raised to power 1. The bases are the same. Then we can pick up the base and subtract their power. Now, can you see that? It's also following. We can just pick one of the base, pick one of the bases, then we subtract the powers. So we can pick one of these two bases and subtract the power. Now, T raised to power minus 1 minus this one. This one is minus 1 minus this. Or you can decide to move this T upward. If you move this T upward now, this power will change to minus. That power also changes to minus. Everything is following. That's what we call mass. So even though you come from this side or you come from this other side, as far as the rules are mathematically oriented, they are mathematics or defined mathematics rules, the thing is going to work well. It's going to work well. So it's not just one way you follow to solve math. No. You don't solve math in one way. You can solve math in several ways using different rules. As far as the rules has mathematics backup, you are good to go. So let's look at this. Then we now have L. Now minus 1 equals what? Minus 2. Now minus 1 means you are going one, you can borrow another one, you will now be going 2. So that's how we go. So let's start the third one. The dimension for force. Let's look at the dimension of force. Look at the dimension of force. Now, what is force? Force is defined as mass times acceleration. That's how we define force. In a way, utilitarian force is equal of mass and acceleration. Remember the second law of Newton's second law of motion. The rate of change of momentum is directly proportional to the applied force. Now, as we also like solve it at the end of the day, now momentum is mass times velocity. So the rate of change of momentum is now mass times velocity over time, and rate of change of momentum. So velocity over time will give us acceleration. So mass times acceleration will now be equal to the applied force. So force is just equal to mp. So m is mass, a is acceleration. So we go on. That's okay. What is the dimension for mass? Capital letter M. Okay, so the dimension for mass is capital letter M. Then times what dimension for acceleration? LT, which is 1 minus 2. So the dimension of force will now be N LT, which is 1 minus 2. That will be the dimension for force. So please take a look at that. So let's look at another one, the fourth one. Let's look at the dimension for work or work done. What will be the dimension for work? Remember, work is what? The product of force and what? Distance move in the direction of the force. Force is the product of work is the product of force and distance move in the direction of the force, which is just force and distance. I'll always mark that. Force and distance. That is work. Work is the product of force and distance move in the direction of the force. So if you apply the force of something and there is no distance move, distance will be 0. So the work will be 0. Why is the work 0? Because the distance is 0. If there is no distance move, 0 times the force will also be 0. It will be 0. So they can ask if somebody will carry a weight of sand in his head and stay one place without any moving any distance. What is the work done? If there is no distance, the work done is 0. So people are very important. Next, what is the dimension for work? ML T raised to power minus 2 times. That is the dimension for work, force, not work. The dimension of force. Then what is the dimension of distance? Now, we come again. Distance is a new term here. Now, what is the unit of distance? Distance is just the difference between 2 points. And it's still something like length. The distance, the difference between 2 points is the distance from here to here. That is the difference between those points. So, once again, what is the unit of now that distance is coming from this length? The unit is still meters. The unit is still meters. So, what do we now do? If the unit is meters, the dimension will be here. So, the dimension of distance is L. Take note of that. The dimension of the radius is L. The dimension of diameter is L. The dimension of displacement is L. The dimension of distance is also L. So, L times L will give us L squared. Give us L squared. And T is power minus 2. So this will be the dimension for work. That is the dimension for work. Now, what is the dimension for energy? Energy. What is the dimension for energy? Now, the dimension for energy is still same as the dimension for work. So please take note of that. What is the dimension for tension? Or what is the dimension for weight? The dimension for weight is still same as the dimension for force. So force and weight and tension has the same dimension because they are all measured in newtons. Then work and energy have the same dimension. Even moments have the same dimension with work and it also have the same dimension with energy. Moment is the product of force and a perpendicular distance. That's what we call moment. Force and perpendicular distance. Now, work is just the product of force and distance moving in the direction of the force, whether perpendicular or not. But moment is now the product of force and distance that is perpendicular to that force. So, product of force and it's perpendicular. Distance will be perpendicular. Or making an angle of 90 in the surface in which you are taking that moment from. So, please take note of that. Moment, force, and energy have the same dimension, which is mR squared T raised to power minus 1. Because energy is measured in joules and work is measured in joules. Moment is measured in Newton meters. But it's still in joules, you don't have Newton meters. You don't measure force in Newton meters. You can measure energy in Newton meters. True or false? It's true because from dimension. Since Newton meters means joules, you can measure work in joules. You can also measure those things. Everything that's measured in joules in Newton meters. So look at number 5. Look at power. Look at power. Let's look at how to calculate the dimension of power. How to calculate the dimension for power. How to calculate the dimension for power. Now, power is the rate at which work is done. Energy is the ability to do work. That's energy. Energy is the ability to do work. We have mechanical energy, heat energy, solar energy, light energy, chemical energy. All of them they are all ability to do work. That's what we call it. Like mechanical energy now we have in terms of we can have it in terms of potential energy or kinetic energy. But let's not digress to that. Now we are into power. Power is not energy. Power is not the same as energy. Energy is the ability for you to even do work at all. You can do work at all, it means you have energy. But power is now the rate at which you do that work. It means the work you have done times the time, divided by the time, not times, divided by the time you used for doing the work. That's your power. For example, now, if both two guys have energy, so for you to know the one that is more powerful, we will check the work they did and check the time used for that work. That will measure their power. So if this one do a work of 50 joules in 10 minutes, the other one did the work of 50 joules in 5 minutes. The one that did the work of 50 joules in 5 minutes is more powerful because that one uses lesser time. So power is just work done over time taken. That's what we call power. Power is the same as work done over the time using for doing the work. So if you have this, you're going to have what is the dimension for work? L squared T raised to power minus 2. What is the dimension for T? That is time is T and raised to power 1. So we're going to be having L squared T raised to power. Since we have T raised to power 2 divided by T raised to power 1, we pick one of the T, then subtract 1 minus 2 minus 1. So we're having L squared T raised to power minus 3. That's what we have. So please take note of that. It's still very, very important. It's very, very important. So please, let's look at one more. Look at one more example. Let's look at one more example. The dimension for stress. That's why dimension for stress. Dimension for stress. Let's that is number 6. So dimension for stress. Now stress is it as force over area. Stress is defined as force over area. Yeah? Now that is the formula for stress. The formula for stress. Okay. Then this stress can also be what is the dimension for force? Force is ml T raised to minus 2 dimension of stress over what is the dimension for area? That's another thing. What is the dimension for area? What is the dimension for volume? Let's see who do those concepts so that we know what we are doing. What is the dimension for area? What is the dimension for volume? What is the dimension for area? Now the dimension for area is, remember, area is length times breadth. Length and breadth are measured in the same unit, this is meters. So you have length times breadth. Length is in meters and the dimension is L. Breadth is also in meters and the dimension is also L. So the dimension will be L squared. So the dimension of area is L squared. Then what is the dimension of let's say volume? Let's say volume. The dimension for volume is length. Okay, let's not check. Volume is length times breadth and height. What is the dimension for L? What is the dimension for length? L. What is the dimension for breadth? It's still measured in meters. It's still L. What is the dimension for height? Height is still measured in meters and it's still L. The dimension will be L cubed. So still think of that. The dimension of volume is L cubed. The dimension for area is L squared. It's very important that you think of that. So the dimension of area is L squared. We will be having our stress to be equal to M. Remember this L is power 1. Then we have L is power 1 divided by L is power 2. So if you pick one of the base, since you have L is power 1 divided by L is power 2, you have L is power 1 divided by L is power 2. That means you pick one of the bases that are the same thing, and you subtract the power. I hope you can remember that rule of indices. So if you know we have not done our indices and the rules of indices we did, is go and watch that video. It's very important. It's going to help you very well in this class. Now see, that is mathematics and physics. They work in line with each other. So you cannot separate maths and physics. They are brothers and sisters. They work in line with each other. So please ensure you do that. So pick one of the base, then we subtract the power. Pick one of the base, then we subtract the power. And you don't subtract the bigger half of one, you don't subtract the second one from the first one. Subtract the second one from this one. That's how you do it. You don't say this one is bigger and that no, you don't do that. Then T raised power minus 2. So that will give us M raised power minus 1, T raised power minus 2. So this will be the dimension for stress. We also have quantities like Newton's modulus, shear modulus, and so on. Charge, and so on. So please take note of those things, they are very, very important. So we are going to halt this class or close this class for this minute. Please ensure if you know something like there's something here you don't get clear, there's opportunity for you. You can watch the video over and over again. In order to get the full details or the full gist of everything we are trying to explain in this place. So please ensure you don't distract yourselves and ensure you are following up in this class. God bless you all. See you guys in our next class.